Okay, good morning, everybody. So we're going to continue from where we stopped last week. Basically, we have already looked at the physical structure, the properties of the MOSFETs, including its at very small voltage applied at the gate and a very small voltage applied between drain and the source. And then we also notice that this device is bidirectional, which means you can use either side as a drain or either side as a source. But for consistency, we're going to have MOSFETs that drain is always on top for especially NMOS. And for PMOS, we already also look at that's just opposite of NMOS. And we also have CMOS, which has a PMOS and an NMOS made on the same substrate. So we are going to start today by looking at the different ways to express NMOS circuit. And later on, we're going to also talk about PMOS. Today's lecture is more on NMOS voltage and current characteristics. There are three different symbols that are interchangeably used for NMOS circuit. And over here, you see ABC, those are three circuits. The difference, as you can see, A represents the physical structure with a body that is connected in the middle. But the directional current from body to the middle is kind of difficult to understand. So therefore, this device model is not used quite often. The middle one shows a MOSFET with the actual current direction for NMOS that flows from drain to source. So that's the current direction. There is a body inside the MOSFET, which is floating right now. But in some applications, actually, you connect the body to the source, which of course it happens. But for our class, we're going to focus on the symbol in figure C. Well, it's simplified. It removes the body connection, and it also has the current flowing from drain to source. So on this diagram, you have drain, and you have source, then you have gate, and you can see the current direction is flowing from drain through the MOSFET and out of source. So this is what we're going to use. The relationship between the current from drain to source, that's called ID, and the voltage across drain and source, and they call it VDS. And also there's a voltage across gate and the source, we call VGS. And those expressions are very much related, and we have to develop the equation for this one. And then we're going to use this equation throughout the book, so throughout this class in the next couple of ways that we look at. Here, I want to illustrate a very simple way how the MOSFET voltage works. And from earlier lecture, you already know that the voltage from gate to source has to be large enough to make the MOSFET work. So if VGS, okay, so let's say if VGS is less than VT, the MOSFET is in off state. It doesn't work. But if VGS is larger than VT, which is a threshold voltage, the MOSFET can be in either, we're going to call it a triode mode, or it could be in saturation mode. And that is depending on the difference between VGS and VTS. The difference between VGS and VTS is called VOV, or overdrive voltage. Some can simply call it over voltage. So it's VGS minus VT. And how do you determine this MOSFET is in triode or saturation? We look at VDS. So if VDS is larger than is, let's start with less. If VGS is less than VOV, it's going to be in the triode region. If VDS is larger than VOV, it's going to be in the saturation. So on the diagram over here, you can see the VGS apparently, because VGS is defined as VOV is defined as VGS minus VT. So therefore, you can certainly derive VGS equal to VTN plus VOV. Okay, and we use a subscript N to represent NMOS. If a PMOS, it will be VTP. So on the right hand of this figure, you see that's the voltage of VGS, which is VTN plus VOV. On the right hand, we apply a voltage. We apply a voltage, which is VDS. So we apply VDS on the figure. So if VDS apparently is smaller than VOV, which is what we have over here, it's in triode mode. If VDS is larger than VOV, it's going to be the saturation mode. In the two different regions, the current and voltage relationship are very much different. And we already illustrated a little bit from our last lecture in chapter 5. Now we're going to continue to look at the voltage and current relationships based on the two different regions. Here, we summarize the operation of a MOSFET, and this table is very important. You guys can copy and paste it on your notes that you can refer to this during exams. You can always look back when you do any problem exercises, when you review examples, or when you do your homework, and you probably have to go back to this figure quite often, or this table quite often, to determine which equation you're going to use. For the interest of E330 and 430, we are mostly interested in operation region, in the saturation region. It's of interest, right? But sometimes we have to determine whether it is in saturation or whether it is in triode. So how do you know? Well, we have to find out whether VDS is larger than VOV or VDS is less than VOV. If it's larger than VOV, it is in saturation. If less than VOV, it is in triode. Okay. It is in triode region. So therefore, now we say, okay, so these two equations are given, and in the triode region, basically the equation is going to be very different from the saturation region. In the saturation region, we have a current called ID equal to 1/2 K N prime, and the weight to loss ratio then times VOV squared. Now remember, this VOV can be expressed as VGS minus VT. Yeah, this is clear. So that's in the saturation region. But then in the this region. So I'm going to write this one to here in the blue color to represent the current in the triode region, which is ID equal to, this is no 1/2. So basically, remember this difference between here. And inside, it will be VOV times VDS minus 1/2 VDS squared. And the equation a little bit more complex. Again, VOV can be expressed as VGS minus VT. From one of the equation I want to write on the right hand of the table is that because we said that VGS has to be in the saturation region. Now I want to write on the side. So VDS, let me use a different color. So VDS on the right hand of the table. So VDS has to be larger than VOV, which is equal to VGS minus VT. So we can say that VGS, oh, we use VTN here. So VDS minus VGS has to be larger than VTN. But what is VDS minus VGS? If you look at the diagram of this MOSFET, so VDS is a voltage from drain to source, and VGS is a voltage from gate to source, which means VDS is equal to VD minus VS, and VGS is equal to VG minus VS. So from here, you can say what is VDS, right? So VDS equal to, I write it on very top. So VDS is equal to VD minus VS equal to VDS is equal to VD minus VS. And then from that equation at the bottom, we know that VS equal to VGS minus VG. So VD minus VD minus VG minus VGS. Okay. So here that we can plug in this VD minus VG and minus VGS. So what you get is VDS is VGD. Okay, so it's VD minus VG minus plus VGS. So from here you can see that VDS minus VGS equal to VD minus VG equal to VDG. So here, which means we have VGD is larger than VTN is the same as VDS minus larger than VOV. So these two equations are going to be exactly same meaning. So these two equations are equivalent. So in the future, if VGD is larger than VTN, VGD is larger than VTN, it's going to be in the trial region. Okay, so this is where we're going to use this very, very much, a lot of them during our classes. So let's get into our next figure. Is that the reason is again because we know that ID from the previous slide, you already know that in either region the current is a function of, like I rewrite here. For example, in the tried region, you have ID is equal to in the tried region you have ID equal to Kn prime times W over L times this VOV times VDS minus 1/2 VDS squared, right? That's in the trial region, and in the saturation region, we also have like this equation here. I don't have to write it, but I mean we can always rewrite it like this, just make ourselves happy or make ourselves. Or in the bottom you have this VOV. So you can see that apparently VTN is a constant once the device is made. So therefore, we always say that ID is always a function of VGS. Or it can be said ID is a function of VOV. Either way, when VGS change, that ID is going to change. So this diagram on the left hand of the screen, it shows very much. It shows very much how the current in a MOS circuit is related to the voltage. The circuit, I can draw just a little just diagram on the circuit over here. It's going to be you can fix one variable and find the current. For example, if you fix VGS, you can find a variable. You can find the current as a variable. Any one of them, like you can find one of them, like VGS. And when you change VGS, the whole curve is going to change. Every time you increase VGS, the current increases. But every single curve is going to be divided into two regions, the triode region and the saturation region. In the triode region, we know that it's VDS less than VOV, or you can say VDG is larger than VOV. Right? In the saturation region, you can say VDS larger than VOV, or VGD. Let me see. It's going to be VGD, not VDG. It has to be make sure that we got the things correct. So VGD has to be larger than VOV, or we have VGD less than VOV. Right? So VGD less than VTN. Sorry about that. So that's the two regions that's going to work. And in our future, that we have to always to find out which region this is going to work, and we can find the relationships. Now, on this diagram, we basically replotted the function of ID as a function of VGS. So it plugging ID as a function of VGS instead of previous slide, we showed the curve, which is a function of ID as a function of VDS, which localize this for single VGS. And you can also plug in another one as a VDS for another VGS. So VGS like 2 is larger than VGS 1, right? But if you use interpolation, you can find out what's the relation between ID and VGS. So when VGS changes, the current will start to change. So also it has to be larger than VTN. So if it's less than VTN, there's no current. So if VGS less than VTN, ID is equal to 0. If VGS is larger than VTN, and it also can go to triode mode, or it can go to saturation mode. And these two satisfy different equation. So it depends on where or how much VGS is more than VTN, and also depending on how much is VDS. So if VDS is larger than VOV, or VDS is less than VOV, so so you can see, and corresponding to this saturation region, and again triode region of this operation. We don't use this diagram very much on this diagram. The most that we use is really the previous. This slide actually we used quite a bit, but this slide we don't use very much. If we look at the relations, since we said we're going to use them mostly in saturation region, So I'm going to have to clarify that this is in saturation region of the MOSFET. Again, this is also NMOS. Because we have ID equal to 1/2 K n prime WOL times VOV squared, or it can be written as VGS minus VT n squared. As you can see, the current is proportional to VGS minus VTN. And VGS minus VTN is the voltage applied at the input side of the gate. So this circuit basically is a representation of this. Maybe we should use that lowercase for consistency. Yeah. You see here, the voltage at the input, VGS on the gate side, minus the VTN. That gives you basically the that dependence of the current ID in the MOSFET. Now, because as we mentioned many times that there's no current, so IG is always 0 because this is an insulated gate and against MOSFET, right? So it's a field effect transistor. There's no current into the gate. So therefore, this equivalent circuit is very useful. Again, these conditions are given in terms of VGS has to be larger than VTN, and VDS has to be larger than equal to VGS minus 15. So those are the conditions have to be met in order for this circuit to work. So this is what we have for the equivalent circuit. So based on here, we can go ahead, start to do some examples. There are many exercises and examples in the book. So from here, we're going to look at this example. This is a very simple example. We're going to say that this NMOS, what they call it is 0.18 micrometer process, which means it's a length. So L, as they said, is given at 0.18 micrometers. You can write this down for your ease of and also W was given as 2 micrometers. So therefore, you can immediately know that W over L is 2 micro over 0.18 micro, and it's roughly 10. It's about just a little bit over 10. So it's about 11. And then the also given was COX was given as 8.6 FF micrometer squared, and mu n was given as well is 450. It's a centimeter squared per volt, and VTN was given to be 0.5 volt. So it asks you to find A and B. So A is find VGS and VDS that result in MOSFET operating age of saturation. And also it says that ID is going to be 100 microamps. Now, guys, remember this picture. Like when you have VDS and ID, you have this relation which is based on. So this is for given VGS, right? And you could also have a different VGS. And you can find the current. Now, at H, we know that ID can be written as 1/2 K N prime WOL VOV squared. And Kn, we can find it. Kn is mu times COX, and that mu is given is 450 times 8.6, right? So that given. So we're going to find some values over here, which is 387, okay? 387 microamp per volt squared. So that's Kn. Now ID is given at 100. So basically, what we're saying is 100 microamps equal to 1/2 times 387. This is also micro. Important because micro is going to cancel, and times VOV squared. So we can find out, okay, VOV squared equal to multiplied by 2, it's going to be 200 divided by 300. We got VOV equal to a square root of this number. That gives you a number which is 0.22. So we find the VOV. So once we find the VOV, we can easily find VGS because, okay, so we don't have space. So I'm going to write it over here. So once VOV is fine, VOV is 0.22. So which means our VGS is going to be VOV plus VTN. And VTN is 0.5, so you get 0.2 volts. And also we said at the boundary, VDS is equal to VOV 0.27. So that's exact what you're going to need is 0. Oh no, I'm sorry, this is a mistake. VOV is 0.22, so it should be VOV is 0.22 volts. Okay, so that's what is given. Now for B, for question B, so that's A, right? So for question B, it asks you to solve for VDS that result in ID is equal to 50 micrograms. Now apparently VGS is kept constant, which means, so if VGS is kept constant, which means VGS is equal to 0.72 volts. And so VOV should not change, which is going to be 0.22 volts, right? So for B. Now, what have we changed? Well, because the current is less. If a current ID is less than the boundary, which is 100 microamps, which means this is going to be in the triode mode. So if it's in the triode mode, we're going to use ID equal to Kn prime times W over L times VOV times VDS minus 1/2 VDS squared. Now you can plug in these numbers together, which means it's going to be, I'm going to write in the middle here for question B. So it's going to be 50 micro equal to 387 micro times W over L is about 11. Oh, actually, in the previous example, I also forgot about this 11 here. So times 11. So this is going to be 2200 divided by 382. And then that's, okay, that's why I make it a small correction. Let me circle it. Small correction over here. So the blue circle gives you the correction of the a little mistake. And I multiply this WOL and then multiply by VOV is 0.22 times VDS minus 1/2 VDS squared. So as you can see here, you have VDS at one variable and everything else is constant. So therefore you can solve for this equation as a quadratic equation. What we found was VDS squared minus 0. I'm going to write it. I'm going to erase this one. So that equation comes down to, I'm going to write over here, just make sure. So it's VDS squared minus 0.44 VDS plus 0.023 equal to 0. And from here, we found VDS equal to two values. One is 0.06, other point is 0.39 volts. At this point, we have to find out which one works. Well, the problem is that if VDS is 0.39, apparently it's going to be larger than VOV, larger than VTN, which is larger than VOV. VOV is 0.22. It has to be in saturation. So therefore, only VDS is going to be in the triode region. This works and this doesn't work. So the 0.06 volts is the correct solution. The 0.39 is the incorrect solution, because if it is 0.39, it will be more than VOV. It's moving to the saturation region. So which means it's not going to be working that way. So this example, now we're going to go to the next. I just want to make sure that we have enough practice. So therefore, we're going to do examples 5.4 as well. So in this example, it says MOS transistor operating edge of saturation, overdrive voltage, and drain current ID. So if that we always doubled, what we must maintain operation edge of operation. What it says here, if I draw the circuit, that you guys probably understand what it means. So for a given VOV and drain current ID, it's opening edge of saturation. So it's operating right over here. So it's going to be a VDS over here and VGS over here, and this is your ID, and then the current, because of the age, we can write down as 1/2 K prime times W over L times VOV squared. So what it says that if we maintain the operation of the age, okay, but we double VOV. So if we double VOV, you see what happens? If you don't change VGS, your current is going to increase, right? So your current ID, if VOV is double, say if VO2 is 2 times VOV1, this is what happens. So if it is supposed to be in age between or at age. Now what you have is ID2 equal to 1/2 Kn prime times W over L times VOV2 square, and it's going to be 1/2 Kn prime W over L times 4 times VO1 squared, because VOV2 is 2 times O1. Because it's in saturation, if we move, and yeah, so basically when you plug this in, you will say this ID is actually equal to 4 times ID1. So the voltage increased by 4 times. And how about VDS? It says what is the drain current and what VDS? Well, because we have to maintain at age, which means VDS has to be equal to VOV, so VDS2, and has to be 2 times VOV1. So this twice. So this is a very simple solution. So if you increase VGS to, well, the reason is that because VGS and VGS equal to V equal to VOV plus VTN. So you increase VOV, VGS is going to increase. So on the diagram, you're going to see another with VGS2, which here is ID2, and here is VDS2. And the blue one is VDS1 and ID1. Okay. So the current would double. When OV doubles, the current would quadruple, and the voltage doubles. This all because the nonlinear relationship of this MOSFET. Okay. So, and then we can move on to look at the next. Let me go to see. The next exercise is probably going to worth to look at it. So this again another n-channel MOSFET operating at a VOV is given. So first of all, you find maybe let's use a red color to make it easier to find out. So this VOV is 0.5, and also it says that IDS is 1 kilo, and VDS is very small. So what is the value of the device transconductance permit Kn, and what is the value of ID? So asking for Kn, asking for ID, and it says when VDS increases to 0.2 volts, from 0.2 to 0.5, right? And also to 1 volt. So here, they already said that's very small VDS. So what it means that, so if VDS is small, which means we compare that to VOV. So if VDS is less than VOV, it's in triode. And the equation is ID equal to 1/2 n prime WL and VOV squared. So this is how you calculate the current. But of course, in this equation, it didn't ask you to calculate current, but it actually tells you that this RDS is 1 kilo ohm. If you remember from our earlier work, is that RDS, how we calculate RDS when it's very small? You're probably going to say, well, that's just a little bit of equation that we said the RDS equal to, it has to be in the triode mode. Well, let me rewrite this equation here. It's the transconductance GDS, and the GDS equal to, we can rewrite this equation, is K n prime times WOL times VGS minus VT. So this is the equation for RDS. Now from this equation, you can find out Kn prime is going to be 1 over WOL VGS minus VT, and also we are times RDS. We can plug in all the numbers to see what we get. So Kn prime, we get WOL. Let's see, WOL. Well, it says Kn. So I'm sorry. So Kn is basically WOL times Kn. So it's going to be just VGS minus VT times RDS, which is going to be VGS minus VT is VOV. So VOV is 0.5. Okay, so VOV is 0.5, yeah. And VDS is or RDS, not VDS. RDS is 1K. So that gives you basically 2 milliamp per volt square. So we got this VKN. So just I want to make correction myself. So Kn is Kn prime temp. That's 2 milliamps. Okay. So that's what you have for the question A. What happens? Now it says this is for very small VDS, but when VDS increases, which now is no longer like 0. something, but it's going to be 0.2 or 0.5 or 0. Or 1 volt. So you know that what happens is when VDS increase 0.2, this thing is still in triode mode, right? So if it's still in triode mode, which means ID can still be found out by doing 1/2 Kn times VOV squared. So it's going to be 1/2, and Kn we found out is times 2, and times VOV is 0.5. So that gives you how much? That gives you 0.5. No, squared. So 25, 25. Let's see, there's probably a mistake somewhere. 1/2. Oh, I'm sorry. So this is going to be in the triode mode. So we should not be using this equation. This is for the saturation. That's probably why the current is not correct. So we're going to have to go back to use the triode. The equation is ID equal to, so it's going to be in triode. It is in triode. Let me actually redo this. So we're going to have 3 different scenarios. So for VDS equal to 0.2, 2 volts, it's less than 0.5, which is the VOV in triode. So we're going to have ID equal to K times, so Kn times VOV, VDS, minus 1/2 VDS squared. So we plug in Kn, which is 2 times, and VOV is 0.5 times VDS is 0.2, then minus 1/2, 0.2 squared. You plug in all these numbers, you will get to this 1.6 milliamps. So that's one. And for number two is VDS equal to 0.5 volts, which is equal to VOV. So therefore, it is in the edge. Okay, it's an edge. You can use this to calculate differently. And of course, the third option is VDS equal to 1 volt. But this is going to be in saturation region. And therefore, we're going to use ID equal to 1/2 Kn VOV squared. And this VOV is going to be 1/2 times 2 times VOV is 0.5 squared. So it's going to be 0.25 milliamps. So that's the last one. For second two, also we got 0.25 milliamps because it's in H. So in the H, you can use 1/2 K times VOV squared. So it has nothing to do with VDS. So we got all the solutions for the first one, 0.5, and the second one, 0.25, and the last one also 0.25. The most important thing is to identify the VDS 0.2 is in the triode region, and VDS is 0.25. It's in H or boundary, and VDS equal to 1 volt. It's in the saturation region. And in the triode region, you can use K times WL VOV times VDS minus 1/2 VDS squared. But for this one, you can use 1/2 KWOL VOV squared. So that's two different equations. So based on that, you can now find out what the actual relationships between the voltage and current. So now we're going to move on to talk a little bit about the relationships with the finite resistance during the saturation region. So basically, so far, what we have talked about is the current ID, VDS, and the relations between ID and VDS, and we talk about the saturation region and the triode region. Again, you guys can memorize by now the equations. And for the triode region, you have ID equal to, and for the saturation region, you have different current. So it's K times WOL, K prime times N times VDS times VOV minus 1/2 VDS squared. And for the saturation region, you have ID equal 1/2 Kn WOL VOV squared. And for that to happen, you will have to have VGS larger than VT, both situations, VGS larger than VT, but also you have VDS less than VGS minus VT, and you have VGS larger than VDS larger than VGS minus VT. So that is what we have so far. As you can see, as soon as it enters in the saturation region, so our assumption is that in saturation region, ID equal to constant. And I want to point this out because this is what we have assumed so far. But in real life, this actually not completely correct. It can actually get into the non-constant region. So what happens is that this will go something like this. And we can actually extend the line to the second quadrant with dotted line. And then that happens, we're going to explain in this lecture. Why that happen? Well, because it's a phenomenon called channel pinch-off. The channel pinch-off point means that it moves away from the drain, reducing the effective channel length. Okay, so if you look at what happens on that in that channel, remember initially you have this channel which is perfectly like even, right? But when you apply voltage, it becomes slightly like this. So it becomes like this area. But when the channel moves a little bit inside, so the actual channel effect area, which means how much electrons like accumulated in the area, it changes. So when it started to change, the drain to source, the current actually is going to be actually different. So this is where we're going to talk about it, is this phenomenon. In BJTs, they call this early voltage. In MOSFET, they don't call this early voltage because it's like a parameter VA, but I just simply call early voltage, just make it across the different devices. The interesting phenomenon is that during the saturation region, that slope of the curve during saturation is actually, if you extend that slope, it's across at a single point. And that single point is expressed by VA over 1 over lambda. That lambda is a effective length reduction. And if we take that slope, we divide by, we reverse that slope, we got the resistance. So basically, this RO equal to that slope. And this is very similar to the diodes. Remember, in the diode, we also have a slope. In the diode, we have this slope, right? We have this slope. And that slope is RD is equal to 1 over slope. So that's the same thing in diode. But in this MOSFET, it's a little bit different. It's a slope of this saturation current curve. And when VGS increase, so VGS increase or VOV increase per se, that slope becomes more and more like slanted, okay? And that current is no longer constant. How do we express current? And we express the current as a function of the reduction in terms of. So the first part is the same, but the current actually is increased by lambda times VDS. So the last part is how much the current is increased. So if lambda is 0, right? If lambda is 0, actually that equation goes back to the original equation. But lambda 0 means VA is infinity. Infinity means all the current ID is constant in that, it is constant in the saturation region. So if ID is constant, the curves are flat, which means VA is infinity and lambda is 0, and it reduces to the ideal situation. But if lambda is not 0 or VA is can be fixed value, and ID is no longer a constant in the saturation region. And this is very important because once you have that resistance, we change the equivalent circuit by adding a resistance. And the reason that how we got this point, well, because in ideal case, we have ID equal to 1/2 Kn prime W over L times VGS minus VTN squared. So that we have ideal case that you have the current and this current in the middle is ID. So and apparently that VDS, it's gonna has nothing to do. It has nothing to do with the value ID because ID is constant. So VDS can change. So VDS change, it doesn't change ID. But in the non-ideal case, our ID is going to change. So it's going to be 1/2 Kn WOL VGS minus VTN squared, and multiplied by 1 plus lambda VDS. So now it has something to do with VDS. It has something to do with VDS. So how much is that thing is important because so we can decompose this into two terms, which is 1/2 chem prime W for L VGS minus VTN squared. That's the first term. And then plus another 1/2 WOL VGS minus VTN squared times lambda. And then lambda is 1 over VA. So lambda is 1 over VA times VDS. So this is the actual equation has two components. And the first component is apparently still the constant current source. But the second term has something to do with VA and something has to do with VDS. So because it has something to do with VDS, so the first term, which let's call this ID Q. So let's call it IDQ. And the second term, we can call it IDQ, right? So we let IDQ equal to 1/2 Kn prime WOL VGS minus VTN squared. So IDQ times VDS times VDS and divide by VA. So if we look at here, we can say, well, we can possibly write this as a function of VDS times IDQ over VA. So what do you think that IDQ over VA, right? Or in other words, what would be if we let something like VA over IDQ, which apparently is a resistance. So we give a name of RO. So we call this like early resistance. So then we can plug in this RO in that expression here, right? So you get now is ID is going to be equal IDQ plus VDS over RO. So this is why you have this RO in that expression is ID, say ID here, in that circuit equal to two components. One component is like IDQ, which is the constant term in the saturation region, and plus another current which flows through RO. That RO definition is VA over RDQ. So in order to find RO, we have to be able to know the early voltage and also the IDQ, the working, the operating current. So by doing this, we can find out what operation that you would get from this non-ideal situation of the circuit. So let me see if I should move on to PMOS. I should maybe do a few more examples. Just give me 1 second. Let me flip this. I want to probably for the main contents, I want to stop it here, and I want to insert a slide so that I can do a few more examples here. Let me do it again. From here. Insert slide. Okay. And yeah. So yeah. So probably we can stop here and do some examples of the main contents, and then we can move on to our our next lecture. We can start to talk about PMOS and the different types of. So let me look at examples in the book to see which one. Okay, let's look at an example of five. We did already 5.4, so we can do 5. We can probably do just a little bit, go over. I'm not going actually uh, the actual numerical solution is probably not so important. Just looking at you guys have the book, so we're gonna say it's an N-channel MOSFET, and the VOV is given at I'm gonna just copy down those values. And oh, actually, we already did this one. Sorry, I'm looking at wrong problem. I'm talking about 5.6. So 5.6 is yeah. So 5.6 is an MOS and transistor. It tells you that it's fabricated 1.8 micrometer technology, which means what it says that this L minimum is going to be 0.18, or it has to be multiple of 0.18 micrometer. Okay, it can be 0.18 or can be 0.36 and so on. That mu CX or K is given. This K n prime is given at 400 and microamps per volt squared. And VA, the early voltage is given at 5 volts per micrometer. Now, look at this unit. It says per micrometer, which means we have to know how much length. If it's per micrometer is 5 volt. So the actual early voltage can be different. So now what is given here is F. L is given 0.8 micrometers and W is given at 16 micrometers. And they want you to find VA and lambda. So because VA is 1 over lambda, right? So if you can find VA, you can find lambda, and VA is is going to be 5 volt per micrometer times L, which is 0.8 micrometers. So it's going to be like 4 volt. So we got the first solution. Of course, lambda is going to be 1 over VA. It's going to be 0.25. And that unit is volt reciprocal. So that's one question. And the second part question was asking for ID. Find ID when the device is operating in an overdrive voltage of, and the given condition was VOV is 0.2 volts and VDS equal to 0.8 volts. So now for this question, we know that since VDS is larger than VOV, so we know it's in saturation region. So saturation region means ideally it's going to be 1/2 K n prime WOL VOV squared. That's again, I'm talking about the ideal situation. So this is going to be 1/2 K M is 400 times W is 16 over 0.8 times VOV 0.2 squared. It's going to give you some voltage, right? And then we need to find the increment, which means we need to find the current, which on the last page we said ID current to be IDQ plus VDS over RO. So this is going to be, and VDS is given 0.8. So then we have to find RO. So RO is going to be, this DQ is some value. We can probably just plug in the numbers and figure it out. So let's say this 800 divided by 0.8. So this 1,000 micro, and then 16 0.04. So there's some values. I have to use my calculator. So IO is going to be VA over IDQ. And VA we already found is 4 volt divided by IDQ is some value. So since RO, so we can plug in this number here to get this value plus this value. And the final solution is going to be 192. Okay, so so that's what we get. We can have, maybe I can have my calculator to see actually we got the correct answer. So here we have 400 divided by 2 divided by 0.8 times 16 times 0.2 times 0.2. Nope, I did everything wrong. Okay, let's talk about it again. So 400 divided by 2 times 16 divided by 0.8 times 0.2 squared gives you 160 microamps. 4 divided by, so it's 4 volts divided by 160 microamps, remember? So this is going to be 0.16. So divide by 0.16. So 4 volts divided by 1.16. That gives you 25 kilo ohms. And so we're going to use 4. We're going to use VDS. VDS is given at 0.8. 0.8. So this is 0.8 divided by 25 kilo ohms. That gives you 32 milliamps. So this gives you 162 plus 32 microamps. So the final solution is 192. So we got the solution correct. The next question asks you, what happens if VDS is increased by 1 volt? Means VDS is going to be increased by 1, means VDS is going to be 0.8 plus 1 is going to be 1.8 volts. Apparently, this is going to be larger than VOV, so still in trial, right? And you can still do the IDQ, which doesn't change, right? So because it's 1/2 Kn prime WOL VOV squared, because VOV didn't change, so therefore this doesn't change, 160 microamps. But that VDS changed, so therefore our ID is going to be IDQ plus VDS now is RO doesn't change because RO is VA over IDQ, which is still 25 K ohms because this doesn't change because VA didn't change, RDQ didn't change. So what we got is 160 plus VDS now is 1.8 divided by RO is 25K again. So let's see how much this is going to give us. So it's going to be 1.8 divided by 25 times 1,000 gives you microamps. That gives you 64. So it's going to be 224. Actually, 0. If VDS increased by 1 volt, so VDS minus, so it's going to be 224 microamps. So so apparently of course the question asks you, no, actually let me see. So IDQ VA is 25, so 1 point increase by 1 volt. They ask about the increment. The increment will be 64, but the solution is 40. I think there's mistake somewhere we might have made. Zero increase by. So I think probably it says increase to 1 volt instead of by 1 volt. If it's 1 volt, it will be 40. It will be 40 milliamps. So if I'm gonna just do quick here. So if VDS equal to 1 volt instead of 1.4, and then the ID will be ID will be 160 plus 1 divided by 25. So that's 200 microamps, 25K. And then the third ID is going to be 40 milliamps. So I think 40 microamps. So 200 micro, and they're going to be third ID is 40 microamps. So this is the solution. Okay, so I think we got pretty much all the homework and examples, so you guys should be familiar. And the next lecture, we're going to go to PMOS and a different set of examples and give you guys a better picture. Okay, so I will stand by for any questions you guys might have. That's great.